Good morning, students. In the last section, we were discussing about the standing wave or stationary wave. So, standing wave or stationary wave is a wave in which energy and momentum transport will not take place. The particles will always be in a particular stage, they cannot move forward. And when we were dealing with the standing wave, we told about 2 points, nodes and antinodes. Nodes are the regions of zero displacement, whereas antinodes are the regions of maximum displacement. So, the distance between two nodes or two successive antinodes, two successive nodes or two successive antinodes will be lambda by 2, and the distance between a node and an antinode will be lambda by 4. Okay. Now, the stationary waves can be produced in many patterns. We can produce transverse stationary waves and we can produce longitudinal stationary waves. We already know the difference between transverse wave and longitudinal wave. So, here now we are going to study the modes of vibration of the standing waves produced in a stretched string. Modes of vibration of standing waves produced in a stretched string. Suppose a guitar string, we tie both the end of the string and we pluck at one end. So, you will be getting a stationary wave. So, before going to that, I have to tell you certain things. First one is called fundamental frequency. The first term is fundamental frequency or fundamental mode of vibration. The minimum possible mode of vibration which is possible by a string is called fundamental mode of vibration. It is not applicable only with the spring, it is not only applicable with the string, it is also applicable to the longitudinal waves also. So, here I am tying both the ends of the string and then I plug the string. I just tie both the ends of the string like this on a rigid support and I am plucking from the middle. So, when I pluck from the middle, what will happen? The wave should come like this, a pulse will create like this and then it will be reflected back. So, this wave and this wave superimposes and they produce a standing wave. This is the lowest possible mode of vibration of a string, and this mode of vibration is called fundamental mode, and the frequency of this vibration is called fundamental frequency. Okay, fundamental mode and the frequency of vibration is called fundamental frequency. So, I will write fundamental mode. Now, you already know what is wavelength. If I draw a wave, this is actually wavelength, lambda. So, here when you look at this figure, there is only half the portion of the wave. You can see there is only a crust, that means only this portion. This portion is actually what? Lambda by 2. So, one full wavelength means one crust and one trough. Here you can see there is only one crust on this overall length. There is no trough. That means the length L is equal to lambda by 2. The length L is equal to lambda by 2. So, what is lambda? 2L. Okay, lambda is equal to 2L. Now, I am finding the frequency of vibration. fundamental frequency of vibration. I will write it as nu. Okay, fundamental frequency, I am making it as nu. So nu is equal to V by lambda 1, because in the previous sections we studied like this, V is equal to nu into lambda. So what is nu? V by lambda. So here I am writing the fundamental mode of vibration, nu is equal to V by lambda 1. And what is lambda 1? Lambda 1 is 12. So I will write V by 12. So this is the equation for the fundamental frequency. Now in the previous sections we also studied like this, the speed of transverse wave in a stretched string can be found by the equation V is equal to root of T by mu, where mu is mass per unit length. That is what we studied, the speed of transverse wave in a stretched string. V is equal to root of T by mu. I am putting that here. Therefore fundamental frequency is 1 by 12 into root of T by mu. Okay. Now the next thing, so the first mode I just wrote like this, fundamental mode. Now second, first overtone, second harmonics. So I will tell you what is meant by overtone, what is meant by harmonics. First just see the figure. In the same string, if the string is pressed at the middle, we are pressing the string at the middle and plucked at 1/4 of its length, then what will happen? You will be getting a wave like this. You will be getting a wave like this, that means one full wave. We are holding at the middle and plucking from 1/4 of the length. So pulse will create here, we fix it here, so another pulse will create there. So this is how a wave is created. And then when I draw the reflected wave, it will be like this. This is the next highest frequency of vibration. Let us compare it with the previous figure. Previous figure, there was one half wave and then its reflected one. So just keep this shape in your mind. Now you can see there are two such kind of shapes. There are two such kind of shapes. So that is the next highest frequency of vibration. So fundamental frequency is the basic mode of vibration, and the next higher modes of vibrations are called overtones. So the overtones are the higher frequencies of vibrations. Okay, overtones are the next highest frequencies of vibrations. So I just wrote it as first overtone, and the next highest frequency will be second overtone, next will be third overtone, like that it goes. Now what is meant by harmonics? Harmonics means it is the integral multiple of the fundamental mode, or integral multiple of fundamental frequency. So fundamental frequency or fundamental mode, the shape is like this. The shape was like this for the fundamental mode. How many such kind of shapes are there? Two shapes, right? This is one shape. In the next mode, how many shapes like this are there? Two shapes. So second harmonics. That is what we call the integral multiple of the fundamental frequency. So the fundamental frequency itself is the first harmonics. So here I can write first harmonics. Fundamental frequency. Fundamental frequency is called first harmonics, and then the next overtone, the first overtone, that is called second harmonics. Okay. Now let us see what is the length here. You can see one full wave is there. Okay, one full wave is present. So L is equal to lambda. L is equal to lambda. So it's the second one, so I just take lambda 2. Now frequency of vibration. Frequency of vibration. So I mark nu 1. That means it is the first overtone, frequency of the first overtone. I mark this as nu 1. Or let us do one thing itself. You may get a confusion if I write like this. So let the fundamental mode, let us mark it as nu 1 itself. Okay, let us mark the fundamental as nu 1 itself. Therefore I can mark first overtone as nu 2. First overtone will be second harmonics. So based on the harmonics we will just continue. So nu 2 V by lambda 2, and what is lambda 2? L. So V by L, and we already know V is equal to root of T by mu. Therefore nu 2 is equal to 1 by L root of T by mu. That is nu 2. Now I am coming to the third harmonics. Third harmonics, or I call it as second overtone. Look how the figure comes. You have to take down all these things, okay? Second overtone or third harmonics. Second overtone or third harmonics. There is 1.5 wave here. This is half the wavelength, lambda by 2. This is another half, lambda by 2, then another half, lambda by 2. So there are 3 lambda by 2s. That is why I called you I called 1.5 wavelength, 3 by 2, 3 lambda by 2. And then I am marking its reflected wave. You will be getting a pattern like this. So here what is L? L is equal to 3 lambda by 2. Lambda by 2. So from there what is lambda? Lambda is equal to 2 by 3 L. Okay, lambda is equal to 2 by 3 L. So a frequency of vibration. Now nu 2, not nu 2, nu 3. Nu 3 is equal to V by lambda 3. So let this be lambda 3. So V by lambda 3 is 2 by 3 L. So 3V by 12. 3V by 12. Or nu 3 is equal to 3 by 12 into root of T by mu. Now similarly, if I take the third, or this is the second overtone or third harmonics. Now when I draw the third overtone, that will be fourth harmonics. So what will be the equation? I am not drawing it, I am just telling you. Third overtone or fourth harmonics. So let us draw this figure also. See, you will get a one wavelength and another wavelength. So lambda by 2, lambda by 2, lambda by 2, lambda by 2. So there are 4 lambda by 2s. That means 2 wavelengths, 2 lambda. And then I take the reflection. I will be getting a pattern like this. So what is L here? L is equal to 2 lambda. There are 2 wavelengths, 2 lambda. And then nu 4 is equal to V by lambda 4. So V by lambda is L by 2. So 2V by L, or nu 4 is equal to 2 by L into root of T by mu. This is how the equation comes. Okay. So when I take the frequency pattern, when I take the ratio of the frequency, nu 1 is to nu 2 is to nu 3 is to nu 4, the ratio will be 1 is to 2 is to 3 is to 4, like that, because you just see the first frequency is V by 12. Okay, first frequency is V by 12. Now look at the second frequency, V by L. That means 2V by 12. So it is 2 times. The first one was V by 12, second one is 2V by 12. That 2V by 12 is V by L. So 2 times. Now you see the third frequency, 3V by 12. So 3 times the first one. Now you see the fourth harmonics, 4V by 12. That is written as 2 into V by L. So it is 4V by 12. That means 4 times the fundamental frequency. That is why I wrote it like nu 1 is to nu 2 is to nu 3 is to nu 4 is equal to 1 is to 2 is to 3 is to 4. So this is how we can produce the higher harmonics in a stretched string, and it can produce all the harmonics like this. That is why we wrote the equation, we wrote the ratio as 1 is to 2 is to 3 is to 4, and the wave formed is a transverse wave. Okay, transverse stationary wave. So that's all about this, and in the next section we will be dealing with the longitudinal standing waves. Okay. So please draw this figure, and this will be asked as a 3-mark question. So you have to draw all the figures and their successive frequencies. Okay, thank you.